Okay, well, thank you very much for coming to this talk, and also thank you to the organizers for inviting me. I'm going to talk about wall modes, but before I do that, I would just like to say that I heard about this meeting originally from Keith Julian. He told me it was going to be a kind of reprise of a meeting in 2018 that he organized at the Lorentz Center in Leiden, which was a very useful meeting. And I think the idea was that this meeting, in some sense, would be kind of revisiting similar topics and trying to see how much progress has been made, since 2018. I'm hoping that some people think that positive progress has been made as opposed to negative progress. But that meeting in Leiden was very good to me because I learned many new things. But I also met Benjamin Favier at that meeting for the first time. And afterwards, we started working together. And so I leave it up to you to decide whether it was a good thing that that we both went to that meeting or not. This is a difficult talk for me to give because John Ornou and Rudy already given my punchlines, and so I don't really have anything to say. So I scrambled the last couple of days to add some extra material that I wasn't going to talk about. So I'm going to start with history. Rudy showed this picture, but this really is the discovery of wall modes in the lab by Tom Rosby. Who is the son of the Rosby waveguide? But I think that was a question from somebody. So the idea here is that you have a convective cell in this region. It's on a rotating turntable, and all of this is kind of the hydraulics that goes with it. And he's measuring essentially the Nusselt number for given temperature difference across the cell. And so the key results that were described in this paper are these. So this shows the critical Rayleigh number as a function of the Taylor number. So the Taylor number is proportional to the square of the rotation. And so the important observation that Rosby made was that the onset, of course, increases with the rotation rate, the threshold for instability. And that's, of course, because rotation is stabilizing. But the surprising thing to him was that this line here for the threshold of the first instability was below the prediction of Chandrasekhar, which is this dashed dotted line. And at the time, he didn't have visualization of the flow, and so he didn't know what was responsible for this. But he says here, this is from his paper, we find excellent agreement between theory, this is Chandrasekhar, and experiment for critical Rayleigh numbers up to some critical Taylor number over here. But beyond that, the fluid becomes unstable at lower Rayleigh numbers. And then he goes on to say this is a very reproducible effect, et cetera, et cetera, et cetera. So this really is the discovery of a new mode of instability that is not in the theory for an infinite layer. And I'm going to call that the bulk problem. And then really the explanation for this was provided in this paper by Buell and Catton. I wanted to mention that because these gentlemen were professors at UCLA. And conceivably some people here might have known them. So this is this paper from 1983. And if you look at this table, so the numbers here in brackets are the mode number that is observed. I mean, this is a numerical calculation of the linear stability problem in comparison with what you get in the infinite domain system, right? So this is a calculation in a cylinder. And you see here that, if the Taylor number here measured by this quantity d is not too large, then the threshold for these different mode numbers, azimuthal mode numbers, is higher than for the infinite layer. But then when you get to this line here, the mode 4 comes in earlier than the infinite domain, right? So that is really an explanation for the presence of a new mode of instability, which is not there in the unbounded domain. Unfortunately, this calculation was done not by solving the linear problem, but using an approximation procedure, like a Rayleigh-Ritz procedure, for finding the minimum eigenvalue of a linear problem. And the assumption was that these modes are stationary. Because in the bulk mode, in the Chandrasekhar theory, of course, the modes that he considered, at least for large enough frontal numbers, they were all stationary modes. And it turns out that in a cylinder, that is not correct. And I think this was discovered by Van Jong and Bobecki and Victor Steinberg in this paper here from 1991. And this is a shadow graph picture of one of their visualizations. And everything is rotating in this talk in the counterclockwise direction. You see this spiral structure. It has wave number 5. And that structure is not stationary in the rotating frame. It actually precesses in the retrograde direction. And so that's a problem with the Buell-Catton paper, because they assumed the solution was stationary. Right? So essentially, their solution of the linear stability problem was not converged. And so we thought, I did this with a student, Rick Goldstein, in Berkeley in 1993. So we actually solved the linear problem. And this is the mode m equals 5, just like the one we saw in the previous slide. And it has the same kind of structure, and it is precessing with a certain frequency in the retrograde direction. So everything here is in viscous units, right? So that's how I'm going to measure the rotation rate. So it's interesting, useful to look at these structures which are confined near the boundary, as you saw. Essentially, the bulk, the interior of the cylinder is empty, right? So these are what, that's what we call these wall modes. And this shows the critical Rayleigh numbers as a function of the rotation rate for different mode numbers. So here is, 0 would be an axisymmetric structure that is not precessing, of course. But then the modes with m numbers 1, 2, 3, 4, 5, etc., they precess, right? And here in the dashed line, just like in the Rossby picture, is the Chandrasekhar prediction, right? And you can see that once the rotation is significant enough, then you transition to these new modes, which are the first modes, non-zero m, that set in for these larger rotation rates. And here is the new information, in a sense, and that is the frequencies or the rotation rates of these modes, right? And not surprisingly, they increase with the angular velocity or the rotation rate of the cylinder. Now, there is another class of modes, and they are the bulk modes, right? These are the modes that Chandrasekhar implicitly was looking at when he looked kind of at the infinite domain system, and this is what they would look like in the same calculation. Here's an m equal 2 mode, here's an m equal 5 mode. These are computed for different aspect ratios, gamma, and these are the first modes that would come in those aspect ratios.
Does Prandtl matter here? What's Prandtl?
The Prandtl number here, let me just think. I think the Prandtl number doesn't enter into this. I'm pretty certain it doesn't come into this. So as you can see, in contrast to the previous modes, these modes, have a non-zero amplitude kind of in the middle of the domain, and they fall off towards the boundary. And I should mention that we've done these with different boundary conditions on the side. So these particular pictures are done with insulating lateral wall. And also, you have a choice of the boundary conditions at top and bottom. You can have no-slip boundary conditions, top and bottom. You can have free-slip boundary conditions, top and bottom. So these, I think, are for the free-slip case. The thing that I would like to emphasize here is that there is a big difference between the behavior of the critical Rayleigh number with the aspect ratio, gamma, of the cylinder. And so here are the wall modes, and you can see that there is a kind of sweet spot here where the wall modes come in. But then as you increase the aspect ratio, the critical Rayleigh number goes up again. Whereas for the bulk modes shown here, you get this kind of oscillation between the critical modes, depending on how many radial oscillations you have, and eventually you asymptote to the Chernusika limit, which is this dashed line over here. Okay, so we have these two classes of modes. These modes also precess. Now, generally, they precess in the retrograde sense, also counter to the rotation of the cylinder. But there are certain aspect ratios where the first mode that comes in actually is a prograde mode. So it's a rather more complicated story with these. But the thing that I should mention is, and I don't have a picture here, but these modes precess slowly relative to the wall modes. And so in this old paper, we actually call these guys slow modes, and then the wall modes, we call them fast modes. Okay. Now, somebody asked a day or two ago, why do these modes precess? I don't remember who that was, but someone, was that you? Yeah. So I'm going to give you a little bit of a kind of mathematical explanation for why they precess, okay? So this is from a paper with Bob many years ago. I apologize for retrieving this old stuff, but I had to think of some new things to add. So what we're going to do is we're going to look at convection in a cylinder, and a cylinder is first going to be at rest. We're going to do that problem, and then we're going to spin it, right? See what the difference is. And we're going to focus, for example, at the temperature. So the temperature in general is a function of the radial position, the angle around the cylinder, and the vertical height z. It's a function of time in principle. And the mode that comes in has a special structure because of the circular symmetry or the invariance under rotation. And it can be written in this form. It's the real part of some time-dependent amplitude, and then e to the minus im phi. Phi is the azimuthal angle, m is the mode number. And then there is some spatial eigenfunction, which depends on the radius, the height, and of course, through that dependence, you're sensitive to the boundary conditions. But the exact form of f is immaterial for this argument. So it works for any set of boundary conditions. And so the task for us is really to understand, how does the mode come in, first of all, and then how does it equilibrate as you cross the threshold, right? You go into the supercritical regime. And so this is a nice way, I think, to think about these kinds of problems, and that's just based on the symmetries of the problem. And in the non-rotating problem, there are two symmetries. You can, of course, take a state, and you can just rotate it to a new position. Okay, and there should be also a solution, right, if the system is symmetric. And in addition, there is a reflection symmetry in vertical planes. Phi goes to minus phi. And you just examine the form of the solution. This is the linear solution, but of course the dots mean the nonlinear corrections, right, in the supercritical regime. So I'm not writing these terms, but everything really depends on the symmetry properties of the eigenfunction here. And what you see is that if you rotate phi to 5 plus a constant, then that is the same as rotating am by this complex number, right? So just a rotation in the complex plane. And so that's a way, if your equations for am are going to be invariant under this operation, it means that all solutions will be invariant under rotations, okay? And then for the symmetry, phi goes to minus phi, well, that is the same as taking am to am complex conjugate. And that's because there's a real part here, right? I mean, we're dealing with a real quantity, the temperature. And then it's a very simple argument to show that am has to satisfy this simple ODE, right? It's first order in time because we have a single eigenvalue that is crossing zero. That's triggering this instability. And so I have am dot has to be some function g, which depends on the amplitude, but it has to be invariant under rotation, so it has to be a function of mod a squared, and it has to be invariant under complex conjugation, and therefore it has to be real, right? So it's a real valued function. And of course times am, right? So this is the equation. So this equation is invariant under these operations. And here I've put this quantity epsilon. It's a parameter. It's a bifurcation parameter. And it's just I think John called it the supercriticality parameter, right? It's just the distance from threshold to the onset of these wall modes, okay? So that's good. So we have an equation. Now, if we're looking near threshold, we can expand that function g in a Taylor series, and then we end up with an equation that looks something like this, okay? Very simple. And it's useful to write this in terms of a real amplitude AM and this quantity capital phi m, which is a phase. And then if you write this equation in terms of real and imaginary parts, you get this pair of equations. The first equation is a pitchfork bifurcation equation. The second equation simply says that, you know, if I rotate my pattern, there's no restoring force. It's a neutral mode, just rotating a pattern. So this is an example of what people in the business call a pitchfork of revolution. Right? So that's, you know, the onset of convective instability. Any convective instability could be a bulk mode, could be a wall mode in a cylinder. Has to look like this. And so kind of the task now in principle is just to calculate the coefficients, right? That alpha and so on, right? I'm not going to do that here, but now, you know, we want to rotate the cylinder, right? And so what do we lose when we rotate the cylinder? Well, we lose that reflection symmetry, that second symmetry that I talked about. And that means that that function g is no longer forced to be real. And so generically, it's complex, right? And so, you know, here is the corresponding Taylor series in that case. You have, you know, these new terms that are going to be proportional to omega, and then delta and beta are functions of omega squared, right? So that all follows immediately from this kind of argument. And then if you decide to write things again in terms of these real and imaginary parts of that equation, you see that the real part gives you, again, this kind of pitchfork bifurcation. But now phi dot is not zero. It's not zero. And here, you know, this is a correction to this frequency of oscillation, which depends on the amplitude. But, you know, if I look for a steady state, I can solve this equation with A dot equals 0, can substitute into here, and that will give me then, if I put everything together, it gives me an equation for the temperature in the supercritical regime. And that equation is going to have a term omega d for drift, right? It's a drift frequency, and the drift frequency is given by this expression. And then I can expand, in fact, in powers of omega as well, these quantities, delta, beta, et cetera, right? So I get a full description of what happens kind of without doing any work, right? That's the nice thing about this, yeah? And so Bob and Van Jong decided to check this, right, in their experiments. And this is from the paper we wrote way back then. So this is how the amplitude increases with the epsilon, the supercriticality parameter. So that's good. That agrees with, you know, with this prediction. I mean, the prediction is a fit, right, because you haven't calculated anything. But you know, the behavior is correct. Here is the Nusselt number that you can get from this. At the threshold goes linearly. Then we have this finite threshold for the frequency. That's omega naught. It's like that will be the onset hop frequency, and then linear behavior beyond that. And then this is how omega naught, the onset frequency, depends on omega, right? So things check out pretty well. And so I think this provides, you know, a mathematical reason why these patterns must precess. They must precess. The question is, you know, do they precess clockwise, counterclockwise, all those kinds of things? And then you actually have to solve the linear problem to determine that. So somebody also mentioned low Prandtl numbers. So one can do the same thing for the low Prandtl numbers. So here is an example of so the Prandtl number does come in. I forget who asked me that. So this is for the axisymmetric mode, right? So the axisymmetric mode when it's oscillating, sets up standing oscillations in the radial direction. So those patterns will not be drifting, but they'll be oscillating. And if the Prandtl number is low enough, you can see that the oscillatory states come in first, and then they terminate, for example, up here when the frequency of oscillation goes to 0. So that's a codimension 2 bifurcation. And so you can understand what happens to these radial oscillations, and then you can look for what happens to states which have a non-zero wave number, right? So they are the ones that would have been precessing in the large Prandtl number regime. And here you see that all the modes are moving now. Here are the corresponding frequencies. Some persist oscillating, over here into large Prandtl number, and they are the wall modes, right? But other ones, disappear when the Prandtl number gets too big, and then the frequency essentially goes to 0 here.
Edgar,
yes?
Could you just tell us what the horizontal axis is for those two plots?
Oh, the horizontal axis is sigma is the Prandtl number. I should have mentioned that. So this is all as a function of sigma. So sigma is 0 here, 1 over here, and then 0.68 is over here. Okay. So again, that's just linear theory, but you can do nonlinear theory in the same way. I'm not going to give any details of that, but this is what you learn. If m is not 0, right, you have a non-zero mode number, then theory tells you that you actually have a bifurcation that leads simultaneously to two types of states. There is this a radial oscillation with a non-zero wave number, and I'm calling that a standing wave. And at the same time, you can generate a traveling wave, which has the same wave number, but it's rotating either in the clockwise direction or in the counterclockwise direction. Okay? So that would be the case when there's no rotation. There will be then symmetry. If you have a wave going counterclockwise, there's also a solution that rotates in the opposite direction. But when you make rotation non-zero, and that's the picture on the right here, this picture breaks up in a certain way. And the theory tells you that it breaks up this way. So the traveling waves are now, they come in at different critical Rayleigh numbers. That's the horizontal axis. I'm calling it mu here, or epsilon, because the rotation, prefers one direction over the other. And then the standing waves turn into a state, which I'm calling a modulated wave, has two frequencies. It's a quasi-periodic state. And then in this case, which is the other possibility, there are only kind of two supercritical cases to consider. In this case, the traveling waves were stable with respect to standing wave perturbations. That's what the solid line indicates here. So that means that, if you went over here and did your experiment, you would find a traveling wave. It would be traveling either clockwise or counterclockwise. That's the non-rotating problem. But then when you rotate the problem, you have a preference for one wave or the other wave, and then this standing wave becomes a modulated wave that bifurcates over here. So in this region here, you actually have a bistability in principle between waves that travel in opposite directions. So that's kind of what you get from this kind of theory, and it's really without doing any work, right? It's just no calculations. And then I'm continuing my kind of historical tour of this topic. There was a nice paper by Hermann and Busse. Was motivated by our work on the cylinder and they said, well, who cares about the cylinder? You have to deal with Bessel functions and it's horrible. Why don't you just take a straight wall, right? Much easier. And so that's what they did, and they made these predictions in the limit of a small Ekman number. So the bulk Ekman number, we were seeing this many times, that goes like e to the minus 4/3, and that increases more rapidly than the threshold for the onset of the wall modes. I want to emphasize this is with insulating sidewalls. These results are modified if you have, for example, perfectly conducting sidewalls, then actually this guy becomes e to the minus 4/3 also, but the prefactor is smaller. So that's been very useful to many people in this community, these results, because we're typically interested in rapidly rotating systems with small Ekman number. There's a paper that for some reason nobody cites, published at the same time, also motivated by our linear calculation, and that's this paper by Cross and Kuo. And they derived this Ginzburg-Landau equation that's valid near onset of instability, again with different boundary conditions on the side. Okay, for a straight wall, this S is the group speed, and so on and so forth. And you have some nonlinear terms, right, specified by these functions G and C3. But they actually calculated all these coefficients. Okay, so that's the more substantial effort, actually, I would say. But it's done just for one set of parameters, parameters from one of Bob's experiments, like Prandtl number 6.4 and so on and so forth. Okay, so now we're going to jump forward to more recent times. So this is from a paper by Bob and Olga Shishkina and Zhang. And so what they have plotted is a number of different computations with different aspect ratios, gamma, different Prandtl numbers, all on one picture. This is the Ekman number on the horizontal axis, and this is the Rayleigh number normalized by the onset for wall modes, right? And so the wall modes set in along this horizontal boundary. In this region, you only have wall modes when you cross this second boundary. That's the onset of the bulk modes that we've been talking about. That's the Chandrasekhar calculation, if you like, for the unbounded system. And then you have all kinds of interesting nonlinear things here, and then eventually geostrophic turbulence. And then if you increase the Rayleigh number too much, of course, then rotation becomes subdominant relative to buoyancy, and you have essentially the non-rotating problem. So some years ago, there was a big thing about a boundary zone of flow. I don't know if that's still a big thing. I'm 100% convinced that it's nothing but wall modes, but in the nonlinear regime. And what this boundary zone of flow looks like depends on the aspect ratio, right? So in this particular calculation, which is from Rudy's group, you just have a m equal 1 mode. So you have a rising velocity on one side, descending velocity on the other side. If you increase the Rayleigh number some more, of course, it becomes more complicated. So here you see the appearance of the bulk mode, right? Filling the domain. And so we did these calculations for their parameter values, partly to make sure that we were doing it right. We didn't quite agree with Rudy's fit to larger Rayleigh number data, but we definitely fit the Busse prediction over here in the red dot. And similar calculations have been done by many other people. I'm not listing everybody here. What's the evolution of the wall modes in the supercritical regime? So just before COVID set in, I visited Benjamin in Marseille, and we worked on this problem there. So what you see here is the cylinder. It's rotating counterclockwise. In the left half of the domain, I'm showing the vertical velocity. You see it's very well confined to the boundary. That's the wall mode. On the right, in the right hemisphere here, you see the corresponding thermal fluctuation that's associated with that. Okay. So that's what's shown in these plots on the left, and then on the right, you see kind of the cylinder unfolded. That's the angle going from 0 to 2 pi around the cylinder. And then time is shown in the horizontal direction. And you can see we start with random initial noise, very small amplitude, and it takes some time for the instability to develop. That depends on the Rayleigh number. And then once it develops, it saturates quite quickly. That's that pitchfork bifurcation of revolution that we talked about. And then it settles here in an m equals 6 state that just travels around, and travels around in the retrograde direction, as predicted, okay? You increase the Rayleigh number some more, it takes less time for the instability to set in. There is some initial coarsening. In this case, it develops into an m equals 4 state. Here we restore the Rayleigh number corresponding to the top plot, and you see that the m equal 4 state remains stable. And so we have bistability here between different wave numbers at the same values of the Rayleigh number. Yeah, Brad.
How big is the azimuthal velocity component? Are these things largely just motions up and down?
I'm going to show some profiles in just a second, so let me tell me if I've answered your question, okay? And so, we can increase the Rayleigh number some more. So now, the wall modes actually are no longer stationary in a rotating frame. And by rotating frame, I mean the precessing frame, right? Not the cylinder frame, but the frame of the wave. And so you can see some dynamics in time. And more surprisingly, you see that persists even when the bulk fills with turbulence, right? So, so what is shown, so we're measuring this near the boundary, so not in the middle of the domain, of course, but near the boundary, the signature of the wall modes persists very clearly. It's essentially, the same thing, except it's now sitting on top of a turbulent state. So that was surprising, that the wall modes don't really care about what goes in the interior of the domain, so they kind of robust in some sense. And so I remembered a talk by Bob many years earlier where he did some similar experiments where he changed the geometry of the container in a non-trivial way, right? And you might say, well, if I put this big barrier here, it's going to kill the wall modes, right? Not so. So the wall mode, remember, precesses in the retrograde direction. It goes around, sees the barrier, says, no worry, I'll just go around. Okay? Right? Like the barrier is not there. And you can deform the domain in many other ways. The wall mode doesn't care. It just goes around the boundary. And that's even true, if you increase the Rayleigh number, and even when the Rayleigh number is large enough that the domain is now turbulent, the interior is now turbulent. You can still see a signature of the wall mode, and it just goes around, No worries, right? So that's an interesting thing. You have this kind of robust structure. So here is just an indication of what the picture looks like. Between these lines is where the barrier is, and you can see that the mode just kind of goes around, doesn't know about the barrier. And that's true even at high Rayleigh numbers. And this is the profile of the flow. You can see here that it's prograde actually very close to the boundary. Then it becomes retrograde, and it's really this part of the domain that's responsible for the precession rate, which is retrograde overall, okay? And this just shows the drift speed. It's minus omega d because it's retrograde. And you can see, in here, I think in blue is the full cylinder, no barrier. In red is the problem with the barrier, and you see no substantial effect on the drift speed. This is the Busset prediction, and this is what the profiles look like for different Rayleigh numbers, very similar to what we had before.
That's a drift speed in angle per time.
Yeah.
Okay, so in linear speed, it zips around that boundary, that barrier really quick, right?
Well, it does speed up when it goes along the boundary. Yeah, and then it returns back to. Yeah, I think that's right. I don't have any movies here, but there are movies of this. So I just want to relate this to something that people have been studying quite a bit. And so these are so-called chiral systems. So here are some examples. You can have particles, charged particles in a magnetic field that all execute cyclotron motion like this. Or you can have gyroscopes which are coupled and rotate all in the same sense. And so people have done experiments on these kinds of two-dimensional problems. And here is an example of the equations that might describe this. This is for sound waves in a system like this, in the presence of this cyclotron motion, and something that they call odd viscosity. It acts on V star, and V star is not the velocity, but the same thing rotated by 90 degrees. So it's like I times V, right? So this term is not actually a dissipative term because of the I. And it's called odd viscosity. So this actually introduces dispersion rather than dissipation. And so if you do a similar kind of calculation, you inject sound waves here, for example, they just travel in a preferred direction, and they are robust with respect to the shape of the boundary. And so this, this is understood to some extent through an area of condensed matter physics called, topological materials or topologically protected states, like two-dimensional semiconductors like graphene, things of that type. And there are some topological invariants, something called the Chern number that you can compute. And if it's non-zero, then you're going to have this topologically protected state that's insensitive to imperfections of the system, changes in the boundaries, and so on and so forth. Jinhan Xie, who was my postdoc, actually computed the Chern number for the convection problem, and he found 1, not 0, right? And so the suggestion was, that maybe the same topological protection describes the robustness of these wall modes with respect to boundary changes. Unfortunately, he was not able to do it for the right boundary conditions. So he has a growing solution that doesn't satisfy the boundary conditions at the top, which was the reason I couldn't do this calculation, because I tried to do it with the right boundaries. But anyway, so there's some suggestion maybe that this topological protection applies. And it also, I think, is relevant to this recent paper by Jeff Vassell, where he looks at wall modes in the rapid rotation limit. This is with Keith and Daniel and various other people, Keith Julian also. And these are the type of states that they compute in the rapid rotation limit. The important thing about this paper is that they say and show that for arbitrary horizontal cross-sections, right? So this is not exactly an arbitrary horizontal cross-section, but the idea is that the scale, horizontal scale, is so small, right, for the structures at the wall that you can change the boundary and the system doesn't know because the scale on which it's operating is even smaller than the curvature in the boundary. So that's kind of what's behind that. So how much time do I have?
You can usually talk for about 10 minutes.
10 more minutes? All right. Okay, 10 more minutes. So we thought, we should, I'm motivated by Rudy's work and various other people. We knew, of course, that the wall modes are a problem. Essentially, they contaminate measurements, Nusselt number measurements, if you're trying to do measurements of Nusselt number, for example, in the geostrophic turbulence regime. We already had some discussion of this in Rudy's talk. And so we thought, obviously putting in a vertical barrier doesn't do any good because the mode just goes round, right? So what about putting, horizontal barriers to suppress the wall mode? Because the wall modes, they extend over the whole depth. And so maybe if you try to squeeze them too much, they're going to be unhappy, right, and go away or something. So this is what was done actually by Louis Terrien in IRFE, whom incidentally I only met in October when I visited IRFE. So this was all done. This was COVID work, So what we do is, we cool the top, we heat from the bottom, and then we have this side wall, but we put a little indentation there of height h and width epsilon, right? So the idea is now if the wall mode wants to form, it doesn't have so much vertical space, right? So that was one case. So we have insulating wall here with an indentation. And the other thing was a kind of simpler version of this, and that is, well, we're just going to zero out the velocity in this region. And that kind of mimics a conducting wall, right? So you have the same conductivity as the fluid because actually you have fluid, right, in that region. So we did these two computations with these two different, so this is done using the Fisher code, the NEC code, so-called. And I'm going to show you a few results of this. So here is the fixed temperature. So that was the insulating indentation, and you can see that there is a certain width, epsilon, of the boundary, and this is the height of the boundary, and you can kind of see that in this region, the insulating boundary condition actually is more effective than the other case. And this is what it looks like in practice. So here is the wall mode, kind of viewed from the side. You can see it very nicely. And then as you put different boundaries, different barriers, you see that that you're decreasing the amplitude of this wall mode, and eventually you suppress it at the boundary. So that was promising, but we discovered that this is not really very sensitive to age, the height of the barrier, and so we thought, well, let's just make it into a very thin barrier, and then what matters really is just the width of the barrier, the horizontal extent of the barrier. And so here is a plot of the critical width that we need to suppress the wall as a function of the Ekman number, and in both cases we have nice Ekman to the 1/3 scaling, which you expect, right? Because the width of the wall mode, is Ekman to the 1/3, right? So why waste space, so to speak, making the barrier even longer? So that all checked out very nicely. Whoops. And then, the question was, how many barriers do you actually need, right? So here is something that we call the effective Rayleigh number. I'm going to define that in a moment, and the effective Ekman number. Here is the threshold for the wall mode in the absence of any barriers. And then here is the situation with different numbers of barriers and different parameters, okay? Then the symbols indicate, no barrier, one barrier, two barriers, etc. And you can see that below here, of course, you don't need barriers. There are no wall modes, nothing happens. But above here, the different numbers of barriers scale on these curves, and these curves are defined by this relation. The effective Rayleigh number goes like the Ekman effective to the -2, and that just comes from a very trivial calculation that just says, if I halve the vertical space for the the mode has, it's going to change the Ekman number by a factor of the depth squared, right? And it's going to change the Rayleigh number by this amount. This d to the 4, because you also change the vertical gradient, right? You have to include that as well. And so all this checks out rather nicely, and so we put that into a simulation, and here you see part of a large domain outside of barriers. So this would be homogeneous geostrophic turbulence. Here you have boundaries along the two sides. So along this side, the wall mode will be traveling this way, and it will be traveling in the opposite direction along the other side. But if you put some barriers in, you see that the wall modes are suppressed, and in eyeball norm, this state looks very similar to the one over there, right? And so you got rid of these pesky wall modes through this process. And how many barriers do you need? Well, you see it here. This is the Nusselt number with no barriers but side walls. You put one barrier, it decreases the Nusselt number. And here you actually fall below the background state. And the reason is, of course, that having these horizontal barriers actually kills some flow along the boundaries. And so you really have a smaller domain than you thought. And so you would expect to undershoot the geostrophic turbulent result. So all of this works out nicely. And the proposal is that this is not a bad thing to do, to try to put these barriers. So I just want to say wall modes are not anything surprising. Somehow, I think the impression here is that wall modes are some special property of rotating convection. I've spent my life working on the Swift-Homburg equation, at least for 20 years. And it's an equation that was derived initially for Rayleigh binary convection as a model. So it has fluid mechanical kind of pedigree, let's say. And so here is a Swift-Homburg equation that has a destabilizing cubic nonlinearity and a stabilizing fifth order. So it's plus u cubed minus b u to the fifth. And you put it in a domain. You put natural boundary conditions, nothing funny with the boundary conditions. And you get a wall mode. Okay, you get a wall mode. And in fact, it's a state that's localized to the boundary. And then there are other states, because this is it's a bistable system. You can also get localization along the boundary, not just to the boundary, but along the boundary, right? So you get these kinds of funny states, and they organize in these so-called snaking structures. I don't really want to spend time on this. So that's a wall mode for the Swift-Homburg equation. And it has various interesting behavior.
Do they persist?
This is the real Swift-Homburg equation. So everything is ultimately stationary. It's a gradient system. But we can make the move. It's another story. But here are the bulk modes, right? And again, because it's a bistable system, you get all kinds of different structures. That fill the domain, that appear in the interior, and you can follow them numerically by, numerical continuation. Here's a bunch more, and this is just a simple scalar equation, right? So the question is, what happens, if you make the problem more complicated? You do convection, right? I would not be surprised if you could see things of this type. All right. How many minutes do I have now? 3, okay. So I like to do asymptotics, and I just want to say a couple of words about equatorially trapped convection. So this is work that was done with Nick Featherstone, actually, and Keith Julian also. I want to end on this because it was done with Keith Julian and Ben Mikkel and Jinhan Xie, whom I've already mentioned. So the idea here is very simple. I'm just going to say this in words. The idea is, we want to look at thin convection in thin layers. So we're going to take a limit of a thin layer. Of course, to generate convection, you have to spin up the system, right? You have to rotate faster. And so that's essentially the asymptotic regime that we perform. Here are some eigenfunctions that you get. So the equator is along here, and this is just kind of the latitudinal behavior of the eigenfunctions. This is what it looks like in the shell, but we unfold it. So because our system has Cartesian coordinates, because I'm looking at a local patch of this, I'm going to go quickly through this. This is just to show you what some of the solutions are. So this would be for the shell, for full shell. And you can see that you have this kind of bending. So this state is precessing in the equatorial direction. In our reduced asymptotic limit, there's no precession. It's a high order effect. But this is what it looks like, in the full shell. Keith would call this, the kind of, he had this nice expression, eye candy, right? Many of you would have heard him talking about this. So he liked these kinds of pictures. I'm not sure how much information there is. The information is actually here. It shows the latitudinal extent of the trapping region near the equator. But the reason really I'm talking about this is because the equator is a boundary. Why is it a boundary? It's a boundary because the vertical component of the Coriolis force vanishes at the equator. So it's a kind of internal boundary. And you expect edge modes, associated with such a boundary. So I'm almost done here. So here's my last slide. So wall modes are a generic property of pattern-forming system, in the presence of boundaries. And certainly in plasma physics, this is a very well-known phenomenon. But wall modes can also be supported by local regional variation, for example, of some material, some fluid property. You can have a localized structure instability at, where you have changing properties. In chiral systems, it appears that, these flows are robust. We don't understand why that's the case. It's understood in these 2D Hermitian problems, Hamiltonian problems, because there are some theorems about that. Our system is driven dissipative, right? It's definitely not a Hermitian problem. And moreover, it's nonlinear, right? So the classical approach like people use for graphene do not apply to this. But, the idea is that perhaps one can move in that direction and try to understand the robustness of these structures. So that's this notion of topological protection that I mentioned. I explained that it's possible in principle to eliminate the effects of wall modes if you so desire. And finally, I wanted to mention that the equator is a boundary when you have a rotating sphere. And in the case of a two-dimensional problem, shallow water theory on the rotating sphere, you can use these topological arguments to actually establish the presence of two modes, two wave modes that are there because of the presence of the equator. And those are the Yanai waves and the Kelvin waves, okay? And why is that the case? Well, it's because the Chern number that I mentioned already is 2. And that is shown in this very nice paper by Antoine Vinay and Brad Marston and the plus. So there's a lot of interesting things which are perhaps orthogonal to what people like to think about here. But I would encourage you at least to read this paper. So thank you.